As we go into this next chapter, 6.1, still working with probabilities, we're going to be focusing more on random variables. And we get to talk about more or two distinct types of random variables later on in section 6.3 next week, which is our binomial distribution random variable and also a geometric distribution. Now, there's a couple types of random variables. You have either a discrete random variable or you have a continuous random variable. Earlier on in chapter 1, there is the definitions of discrete and continuous. We've used discrete and continuous in algebra classes before. Discrete were basically your whole values, your whole number values, and then your continuous were all the extra little decimal places. And so discrete were like your shoe size, or just using your counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. Continuous were your measurements. So it's your weight, it's your it could be the length or your height. We all vary in the height, and then we get to the little decimal place values. It's the speed of objects, the volumes of stuff, the areas and stuff. Those are the difference in a way of between them. A probability model describes the possible outcomes of a chance process and likelihood of those outcomes will occur. We talked about that before. The definition of a random variable takes numerical values that describe outcomes of some sort of chance process. A probability distribution of a random variable gives its possible values and the probability of each occurring. So when we see these distributions, they're going to be in this, as we scroll down a little bit here, they're going to be in this format of these tables. Those tables that we see there, those are our probability distributions is what we see. We see them more often with the discrete variables than with the continuous, just because your continuous random variables, since they include all the decimal places, it's hard to create a table for those. And so we usually don't associate the probability distribution template of a table with a continuous one. It's usually associated with discrete. A discrete random variable, X, takes a fixed set of possible values with gaps between them, which means none of the decimals, okay, in a way. So we're doing like whole numbers like 0, 1, 2, 3, 4. Like when I'm flipping a coin, can I flip a half of the head? And so typically when we do these things, when we do tables for probabilities in this chapter here with discrete random variables, we will isolate, if I flip a coin 5 times, then I look at the variable X is getting a heads would be my desired event. What's the probability of getting a heads? And then I would go through and figure out with a tree diagram or whatever, what's the probability of getting no heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads when I'm flipping the coin 5 times. Okay, and so in order for that to be a valid probability distribution, we had these stipulations before. Each probability has to be between 0 and 1, each individual probability. Remember, probabilities cannot be negative. The sum of all the probabilities has to add up to be 1. And this is where taking out we have that closeness of the place values. If we don't go out enough digits, sometimes it's going to be off by just a smidge, and that's okay. To find the probability of an event, we just get to basically, if it's an individual event, what's the probability of getting 2 heads? I just look at its probability. If it's at least 2 heads, then I start adding up things that are associated with that, at least part or at most to get the event that we're doing here. So some of these can get pretty complex as we look at when our events involved more than just one thing, when it's adding up several of the cells. And that's what we get that we're going to eventually do here in a moment here. In 2010, there were 1,319 games played in the National Hockey League. Imagine selecting one of these games at random, and then the random selecting one of the 2 teams that played in the game. We're going to define our random variable X is equal to the number of goals scored by a randomly selected teams. All right, so there's what our X is. Our X is the number of goals scored, is what our X is. Now, the table here below shows us what the probability distribution is. So the bottom line shows what was the probability that a randomly team selected scored no goals, 1 goals, 2, 3, 4, all the way up to 9 goals. They asked us to show that this distribution for the X, is it legitimate? So we go through and we look at, this is where we don't have to list it, but we look, okay, that's between 0 and 1, 0 and 1, 0 and 1, 0 and 1, blah, 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 blah. Hey, each P of X is between 0 and 1. And then the second thing I got to say, what does that sum add up to be? So what does, and again, when I look at it again on a free response question, you're going to have to indicate that. If one of them wasn't, we say, hey, not valid because one of them was not. Then we would say, all right, the sum of the P of X's. And on this case, for showing work, we can just start off with just a little bit, like show the first couple, and then dot, 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 and then I can put in the last one, and then I do equals. So when I'm looking at showing my work for getting credit for showing work, you just saying yes or no is not going to get you points. You're going to have to support it somehow. So supporting it with each P of X is between 0 and 1, that gets credit for that first characteristic. Doing what I just wrote there, the sum of P of X equals, I took the first couple numbers plus dot, 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 indicates to the reader, hey, I'm adding up all the next of them together. I'm going to stop when I get to this last number. And then what's my answer? Okay? This is where we can go to the calculator and we can just start typing them in and adding them up. Okay? And so with that in mind, I believe that adds up to be about 1, if not exactly 1. Okay? If you want to check, you can check. But it pretty much comes out to be 1. So yes, this is a legitimate one. So yes, legitimate. They ask us in the next part to make a histogram of the probability distribution. Again, notice how they have number of goals scored on the bottom, in a game, and then on the vertical is the probability. We only had to go up as high as what we needed for the biggest probability that occurred. We don't have to go up to 100 or to 1. And then now it's just a matter of sketching in. 0.061, that would be just a smidge above that line. Next one, 0.154 would be somewhere about almost to the 0.16 line. Number 2, 0.228, so that's almost to 228, so that's almost halfway to 0.23. And then we get to go 0.229, so that one's just a smidge taller. And then we get to drop down to 0.17, somewhere about right there. Then we go into 0.09, so right about there. And then we drop down to 0.041, so just right above the 0.4 line, 0.04 line. Then we go 0.015. Now we drop down big time. Now we're at here. Then 0.004, which is like maybe there, and then the 0.001 is just like a little tick mark. This is just one little line. Again, that's a rough sketch. They asked us to describe what we see. All right. So remember, typically when we're describing what we're seeing, we're always referring back to the socks from earlier on. So when I look at shape, outliers, center, spread, shape, as we look at the first one, it looks like it's skewed right. Looks like it's skewed right. Outliers. Technically, we don't have any information to determine is 9 goals an outlier or not. We don't have all the individual datas. So, this one we can't tell. So it would be okay to leave it off as a descriptor. But you can also say, hey, can't determine if there's an outlier because we're not given individual data values in our table up above. Our center, there appears to be a peak around 2 to 3 goals. And that would be basically, our mode when we look at the frequency. Those are where there is a higher percentage, 22%, to basically 23% rounded for both of them. So that's where we have our greatest peak. And then our spread, it has a range of 9 goals. Again, we don't have enough information to look at IQR for us because we talked about when it's skewed, we use IQR. Don't have enough information for that. All right? And so with that in mind, then we use the range to describe it. Max minus the min. Again, don't have all the information to calculate what the median is. I would say it's probably somewhere, if you look at, if we add up the first, we can see roughly where it is. If I take 0.61, where's my calculator? I don't know why I'm doing it by on top of my head. Come on, calculator. If I take 0.061 plus 0.154 plus 0.228, I add those together, I got 44%. So that tells me somewhere in 3 goals is where my median is going to be. Because what does the median have to the left and right of it? What percent of the data? 50%, right? Median is the middle, so half is to the left and half is to the right. So somewhere in the 3 goal column is where our median is going to be. So we could say that. We have enough information to say that the median is 3 goals. The median is 3 goals. There is enough information to say that. Because, we can add up and say, hey, if the first 0, 1, and 2 goals gets me to 44%, obviously 50% is going to be somewhere in that 3 goal part. Well, if we had all the data values and list them out numerically, from smallest to biggest. Next part, it says, what is the probability that the number of goals scored by a randomly selected team in a random selected game is at least 6? So what is the probability that X is at least 6? That's greater than or equal to 6. And this is where we got to be careful with our at most and then more than and less than. So that would be taking the 6 goals, 0.041, plus the 7 goals, plus the 8 goals, plus the 9 goals, because those are all the at least 6, and adding them up, and I get that it's approximately 0.061. There is a 6.1% chance of randomly selecting a team in a randomly selected game, and they have scored. There's more than 6 goals scored, or they scored more than 6 goals. Any questions so far? All right, the mean or the expected value. We're going to need to, again, we have a lot of vocabulary in our course, and when we see the words expected value, we want to associate it with the mean. The mean of whatever it is. Mean is equal to expected value. So the mean or expected value of any discrete random variable is an average of the possible outcomes, with each outcome weighed by its probability. So with that in mind, when we think about it, before today, if I took that hockey thing situation and I took all the goals scored, added them up, divided by how many total items I had there, sample size, that would have been my average. However, when it's a discrete random variable, it's not just adding up each event of 1 goal plus 2 goals plus 3 goals and 4 goals. It is actually, we take each individual event, multiply it by its probability, and that's where we call it a weighted. We multiply it by its probability, then we get to add up what it is. There's no dividing. So to find the mean or expected value of a probability distribution, a discrete probability distribution, we basically take each x value, multiply it by its probability, and then add up all those answers together. And that's what our expected value is. The capital EX there, that is the notation for expected value. Again, we have a lot of different notations that we have to use, and we will see. So capital EX or capital EY, capital EY is the expected Y, the expected value of the Y's is what that would be. If you had an event that was based off of, Y. Now, how do we interpret it? Here's another script we get to put into our memory. If we perform many, many, many trials, if we look at many, many, many NHA hockey games, we would expect the average number of goals scored is this. Okay, so we would use our context of our problem as we do it. Since we use mean as a measure of center as a discrete random variable, we'll use standard deviation as a measure of spread. The definition of the variance of a random variable is similar to the definition of the variance of a set of quantitative data. Suppose X is a discrete random variable whose probability distribution is modeled by that table, and mu sub X is the mean of X. The variance of X, we can find that, the var of X, the variance of our distribution of X, denoted by sigma squared sub X. We can go about taking each of the X values, subtract the mean from it, square it, multiply it by the probability of that one, then add the second X value minus the mean squared times its probability, blah, 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 blah. And then eventually we get what our variance is. Okay? To get the standard deviation of a random variable, all we do is take the square root of what we just did for the variance. Variance, the standard deviation is always the square root of the variance. The variance is always the square of the standard deviation. Again, doing it by hand takes a while. Okay? We are not asked to do that a lot by hand. Typically, it's going to be calculator using it to our technology to our benefit to get things done quicker. Our interpretation of the standard deviation. We don't have to usually interpret the variance in this course. Okay, the interpretation of the standard deviation, we say on average, the number of goals scored in the NHL problem basically will differ from the mean of, we state what the mean is, and then by about, well, what is the standard deviation? So that's our little phrasing we try to memorize and recite as we do things, and as we do a free response. We're also looking for those as the key way on the multiple choice to pick answer choices. So here is a problem done for it. We're just going to walk through it. You don't have to do any of the calculations. We just get to walk through it. In 1952, Dr. Virginia Apgard suggested 5 criteria for measuring a baby's health at birth. She developed a 0, 1, and 2 scale to rate a newborn on each of the 5 criteria. A baby's Apgard score is the sum of the ratings on each of the 5 scales. What Apgard scales are typical? To find out, researchers recorded the Apgar scores of over 2 million newborn babies in a single year. Imagine selecting one of these newborns at random. That's our event. So define the random variable is the Apgar score of a randomly selected baby 1 minute after birth. The table below gives the probability of distribution for that X. The probability of getting a score of 0, less than 1%, 0.1%. The score of 1, 0.6%, then 0.7, 0.8, and then we jump up to 1.2% would have a score of a 4, 2% would have a 5, 3.8 to a 6, 7, for an APGARD score of 7, 9.9%. Then we jump up big time. We see a greater frequency of newborns having a score of 31.9%, then 43.7%, and then back down to 5.3%. So, that's telling me that there is a greater frequency of APGARD scores that are kind of occurring in that, especially the 8 and 9 range. As we get away from 8 and 9, 10 is the max, or what they had at least in this thing. Don't know if you can get bigger than 10. I guess 2 times 5 is 10, so that's the max score you can get. So, looking at 5%, not many have a perfect 10, if you want to call it, on that score. A greater percentage is in here, and that's where our mode and peak would be. So compute the mean and standard deviation for each. Again, to get the mean, the expected value, they took each score, multiplied it by its probability. That's what we're seeing in this first part. And did that for each one. Got those answers to multiplication problems. Then added them up, and we found out that the mean, the expected value, E of X, was equal to 8.128. That was the mean or the expected score we're expecting the kids to have. The expected score on a randomly chosen child born in that year would be 8.128. Again, here's the interpretation. The APGARD score of a randomly selected newborn is 8.128. This is the long-term average APGARD score of many, many, many random chosen babies. Now, you could start the interpretation. Remember, it talked about in our interpretation, if we randomly select many, 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 many babies, the average APGARD score, we would expect the average APGARD score to be about 8.128. So there's a couple different ways you can rephrase it. You just want to make sure you specify that you're doing many, many, many randomly chosen babies, or whatever your variable is. Your standard deviation, they took each data value, each score, subtracted the mean from it, what we just found, times it by the probability. Of course, they squared it, then times it by the probability. Did that for each one, added those up, took the square root. Here's my standard deviation of the distribution. Again, if I wanted the variance of the distribution, my variance of X, well, that was the 2.066. All right, so that number right in here, that was my 2.066. That was my variance. That was my variance of X. Because in order to get the standard deviation, you had the square root. Our interpretation of the standard deviation, on average, a randomly selected baby's APGAR score will differ from the mean of, we specify what the mean is, 8.128, by about 1.4. Okay, is what we can say there. Again, we're going to get practice doing this live here in a minute. How do we get to calculate the mean and standard deviation of a discrete random variable when they give us on the calculator when they give us the table? We're going to put the X values in list 1. We put the probabilities of each of those things in L2, so make sure you match them up carefully. Okay, otherwise you change what the mean and those things are. Then what we're going to do is we're going to go to one var stats. We're going to let L1 be the our category stuff. So we're going to make sure our L1 is in list 1 is the first. What we have in L2 goes into the frequency list. Now, we've always left the frequency list blank when we did one var stats. Now we get to use it. Okay? So I'm going to go ahead, as some of you have already started, I'm going to split screen, and I'm going to grab a calculator, and I'm going to start putting that next example in there, and we'll talk about it. So I'm going to go put in that next problem in the table, and then we'll talk about it there. Okay, that was the hockey one. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Wow, how did I get 15 in there? 7, 8. Well, 7 plus 8 is 9. There's a 15, so that's what I did. 9. There we go. All right, coming up to the next column, making sure I didn't have happy fingers there. So 0.061, 0.154, 0.228, 0.229, 0.173, 0.094, 0.041, 0.017 or 15, sorry, 0.004, 0.001. All right, sweet. All right, so I got my data in there. Again, just going to scroll back here, just look at the problem here, and as you type, you can keep typing ahead of me. In 2010, there were 1,319 games played again in the NHL season. Imagine selecting one of those games at random, and then we randomly select one of the two teams that played in the game to find the random variable such and such. They asked us to compute the mean and standard deviation of the random variable x, okay? And then they want us to interpret in context. All right, sweet. So now we got our stuff in L1 and L2. I'm going to do second mode to quit the screen. I'm going to press stat. I'm going to go to one var stat underneath calculate. I did put my x values in the L1. The frequency list, I arrowed down and pressed second 2 to put L2 there. This way, we need that there so that it'll calculate our standard deviation is what we need it there for, okay? So then I go down to calculate, hit enter. And then with that in mind, and that's why I've made a little note up here, they actually don't show S sub x on that screen. We have to grab the lowercase sigma x. We have to go there to grab that one. So my mean, my expected value, my EX, is equal to 2.851. We want to use EX. We don't want to use X bar as a indicator, as a script. We want to use our expected value is that. We know they all mean the same, okay? We know E of X is equal to mu X, which is equal to X bar, but we make sure we highlighted that the expected value is that. My standard deviation is 1.6324. Now I get to go through and interpret, write the sentences trying to use my script. So here is what I have written to kind of put down there as an example. See if I can squeeze it in here. After viewing, oh, there we go. After viewing many NHL games, we would expect the average goals scored, to be about 2.851. I'm going to switch colors as I do the standard deviation. On average, the goals scored will vary from the mean. Specify what it is, 2.851 by about 1.6324 goals. Again, I know it's going to be a lot of scripts to memorize when you look at the course of the year for the AP exam. The best thing I can suggest is as we keep progressing, come back and revisit some of this stuff. From time to time on the online, go on the online book and look at it, maybe a chapter test or the chapter review problems, because we usually don't do those. Look at the odds and try to practice them from time to time, because then you can check to make sure, are you writing the right thing and so forth as you're doing things, okay? And you can check yourself as you look at prepping for that exam later on. We'll get a ton of practice in April, but it's just, you know, and it's maybe one of those things where you start your own little page here in OneNote and you title it scripts. And you title the title like chapter 1, you know, what we did in chapter 1. Here are the scripts I need to use. Chapter 2, chapter 3, here in chapter 6, we would put these down there. And just have a quick little reference guide to go back to as we keep progressing. You can just go right to that cheat sheet guide when we start doing the cumulative review to keep things, you know, get things in mind. Okay, so, you know, that might be a good thing to start doing. Remember, you still have access. I don't know if any of you actually have been going into the doodle reviews. And remember, I had the doodle reviews kind of done for you, and I have a cheat sheet page there. Okay. You know, remember, those are out there for the different things. Some of them have the scripts on there. Maybe you want to write the scripts on some of them. Okay. That way you have them there as you do stuff. So, but just to remind you, that's there if you want it. Don't have to. All right, here's an example we get to you again. You can work ahead of me. This is the last one of a discrete random variable. Then we're going to get into a continuous random variable. Again, today's not a long day. Tomorrow is a lot longer because we talk about transforming our random variables. What happens when we add, subtract, multiply, divide stuff, with the mean and the standard deviations and those things. So tomorrow's a little bit more crazy of a day. A great way to finish up a week. So in an experiment on the behavior of young children, each subject is placed in an area with 5 toys. Past experiments have shown that the probability of distribution of the number X of toys played with by a randomly selected subject is as follows. So 3% for no toys, 16% for 1, 30 for 2, 23 for 3, then 17%, and then 11%. So they asked us to calculate the mean and standard deviation and then also interpret them. So again, you can work ahead of me on this one. I'm gonna talk a little bit softer so I don't deafen people listening to the video. Some of you probably realize that you had to turn down your volume when you listen to my videos. And then I'm going to go to here. 5 was the most, so there we go. Already got the 0, 1, 2, 3, 4, 5 in there, so stat calc 1 var stat, set up the same way I just did it. L1 for my X values, my probabilities are in L2. Sweet. And here we go. So my expected value, E of X, which we know is mu X, which we know is X bar, is equal to 2.68. My standard deviation of X. And we do want to have those subscripts of the X in there because we start dealing with more than one set of data values, sometimes comparing situations. So we want to make sure we get in the habit of writing that. That is equal to 1.3106. Now my interpretations. After observing many children we would expect that the average number of toys played with to be about 2.68. All right. Now we go over here talking about the standard deviation, which we said the standard deviation was 1.3106. On average, the number of toys played with will vary from the mean of 2.68 by about 1.3106 toys. Now, it would be okay on that one in the explanation. They wouldn't dock you since the mean went out 2 decimal places. The expected value went out 2 decimal places. It would have been okay for you to say 1.31 toys. That would have been okay. Usually you go out as many decimal places as the mean for the standard deviation in the explanation. And since our calculator just gave it to the 2 decimal places because it was terminating, it's okay to go that far. And on the previous one, we could have stopped at the 1.632 since it was a 3-digit decimal for the mean on the previous one. Awesome. Any questions so far? All right. A continuous random variable. Again, we just tackled discrete. Continuous means I got all the little decimal places in between, all the measurements between 2 whole numbers. Okay? So discrete random variables commonly arise from situations that require you to count something, like number of heads, number of tails, and so forth. The AppGuard scores, you couldn't have a half of a score. Situations that involve measuring something often result in a continuous random variable. A continuous random variable, x, takes on any value in an interval of values. The probability distribution of x is described by a density curve. The probability of any event in the area under the density curve and above or below the value of x that make up the event. The probability of a discrete random variable x assigns a probability between 0 and 1 to each possible x value. A continuous random variable y has an infinitely many possible values. All continuous probability models assign probabilities of 0 to each individual outcome. Only an interval of values will have a numerical other than probability. So that's why we're saying on that. What that one's basically kind of in a loose way of saying is, we're not going to see a table associated with these things like we did with the discrete, because we don't have the exact probability for every single little decimal possible thing of a 1.1, a 1.2, a 1.29. We don't have those individual things doing there. So here they're telling us they're going to ask us these ranges, and it's going to be an interval. What's the probability it's going to be between this and this is what it's going to do. Now, I'm already starting to think about, well, when did we talk about probabilities with a continuous situation? That would be going back to chapter 2, when we started learning about z-scores. And we had the z-scores weren't just whole numbers, they were actually tenths and hundredths. And then we also took that into that normal distribution. And we used that normal distribution of the area under the curve. That was our density curve. That was our first introduction to density curves, was back in that chapter. So that's what this kind of little description about a continuous random variable is kind of making you try to remember. We don't describe it with a table with distinct percentages. It's the area underneath a density curve, which has infinite number of possibilities for what the probability could be. So that's what that's kind of reminding you of. And as I try to find there it is. So I'm just going to make a little note there for Gene there. This is remembering our normal distribution stuff. That's what that's reminding us about there. Now that I gave that hint away, that lets us know as we do some of this continuous random variable probabilities, what's the probability of this occurring? I'm going to go back to using that probability, that normal CDF feature to find these answers. So here is an example of the heights of young women who closely follow the normal distribution. Notice normal distribution with a mean, a mu of 64 inches, standard deviation of that. This is the distribution for a large set of data. Now choose one woman at random. We're going to call her height Y. If we repeat the random choice very, very many times, or many, many, many times, the distribution of the values of Y is the same normal distribution that describes the height of all young women. So find the probability that that the chosen woman has a height between 68 and 70 inches tall. So again, they told us that the mean of Y, okay, they told us that our mean was 64. Standard deviation was 2.7. In our picture of our normal curve, okay, we're trying to find this little area, probability right there. What's the probability that it's between those two numbers? So here we go with our normal CDF. We got our lower bound. That's the 68. Our upper bound is the 70. Our mean is 64, and our standard deviation is 2.7. And then now I'm ready to bust out the calculator. If you forgot where it was, it's second vars, option number 2. Hit enter. Now we type in, we said we had 68, 70, mean of 64, and a standard deviation of 2.7. Again, they're not standardized, and that's another way you could do it. You could have standardized the 68 and 70 and then just use the 0 and 1 for mean and standard deviation. But again, we don't have to. Let's just use what they have. It makes it easier on us. Oh, get out of there. And here we go. So we get 0.0561. So there's a 5.61% chance. Okay. So I'm going to write that in a little sentence here, underneath of it, as I just describe or interpret what that means. There we go. The probability that a randomly chosen woman has a height between 68 and 70 inches is 5.61%. again, we just don't say, hey, the probability is this. We always have to look at interpreting it in a sentence. So we want to make sure that we specify that it's a randomly chosen woman, okay? Because that's what we talked about in the design of what we did here. That as the data was gathered, and they did it many, many, many times, the probability that a randomly chosen woman has a height between those two height amounts is about 5.61%. And again, does that make sense for what the slice of that curve looks like? Is it a small percentage? Yeah, so that was reasonable. Means to me, it doesn't look like I did something wrong. Now, if I had something that was, highlighted like this, it was all this red stuff, and then it says 5.61. I'm like, okay, something's wrong. That doesn't look like 5.61. Okay, so we always make sure we double check when we do stuff, because then we can catch goofy mistakes when we type stuff in. One last example here, and then we're done for the day. The weights of 3-year-olds females closely resemble a normal distribution. I always like highlighting that, not only in this chapter but future chapters, because when I see that it follows a normal distribution, when I'm trying to find probabilities at some stage in a problem, I can refer back to the normal distribution. I can do the normal CDF. Okay, so that's my point of why am I pointing that out, because hey, that helps us with some of the stuff we got to do 3, 4, 5 chapters from now. So it has a mean of 30.7 and a standard deviation of 3.6. So mean is equal to 30.7. Standard deviation of 3.6. Randomly choose one of the 3-year-old females and call her weight X. Find the probability that the randomly selected 3-year-old female weighs at least 30. So what's the probability that X at least 30 is greater than or equal to 30? Again, we need to make sure we can convert the inequality phrases into inequality symbols, especially for this chapter, so we know where am I doing stuff. Now, based on what we did earlier in our course, we know the mean is in the middle. We know 30.7, and then we can start adding the 3.6 to the right to find our deviation, our standard deviations away. So that would be like 34.3 would be the next one. And then, we could keep doing, if we wanted to keep doing that, then it would be like 37.9. And on the other side, I would subtract. So if I subtract 3.6 from 30.7, I get 27.1. I think I did that right in my head. Okay. Now, here's our challenge as we look at shading. And shading is, again, we talk about always putting graphs up there and displaying stuff. So if I was going to illustrate this to my grader, I would label out the distributions, the standard deviations. And then where is 30? 30 is just a smidge to the left here. Not much, just a smidge to the left of that mean. And then I'm going to indicate it's everything to the right. That's what we're trying to find the probability of. And so again, mentally, now that I see that picture, I'm like, okay, from 30.7 to the right is 50%. I'm just a smidge to the left of it. So I should have something bigger than 50%, but not really big. Okay, so, maybe 60% is my cutoff. So if I get a data value that's less than 50% as an answer, or way bigger than 60%, I got to go back to see if I did something wrong. Okay, that's where drawing these pictures kind of help make sure we're thinking the right thing as we go to calculate. So now we go in, we say, all right, normal CDF, because it said it was a normal distribution. It followed a normal distribution. Normal CDF, lower bound is 30. Upper bound, you can do something really big. Again, it's a 3-year-old. You're not going to have a 3-year-old be 10,000 pounds. 100 pounds would have been a cutoff, is what you can do. But I usually don't worry about the upper bound or something. I just put a big number always, so I don't have to worry about which scenario do I change it. It's just easier that way. The mean is equal to 30.7, and standard deviation is 3.6. Again, it's not going to change it tremendously by doing that if I did 100 pounds or 1,000 pounds. 10 pounds, yeah, that's going to be a difference. It's not going to give me enough area. So that's why I wanted, 10 pounds is way less than what my mean is. So we should never be below our lower bound. That's when you'll get really crazy data. So, boom, 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 boom. Here we go. Second VARs, normal CDF. And then we get to type in 30, 10,000 pounds, mean of 30.7 and 3.6. Go through and hit enter a couple times, and it is 0.5771. All right, I always try to get in the habit of rounding to the fourth. I'm done with calculation, so I'm allowed to round. So now as I go to an interpretation, the probability that a randomly selected 3-year-old female weighs at least 30 pounds is 57.71%. And again, that is within my expected, what I was thinking. I was thinking a little bit more than 50, should be less than 60. Now, that's pretty close, but again, that's because of what our standard deviation is and what our mean was. And so, I mean, so it was close to my 60 cutoff, but again, I didn't get anything more than that, like 70%, so I knew I'm okay on what I'm doing.